Yeah, I really got excited after hearing the keynote from Joe, and it's always good to hear the history from Jim. And thank you, Dave, for inviting us here. It's a pleasure to be here. Okay, so the verification 3.0, I feel that it's a really important endeavor, and what we bring in as a company is the solutions for minimizing the errors caused functional by the functional specification. Okay, so we've seen the survey from our industry about the functional spec as being one of the main culprits when it comes to SOC functional flaws. Okay, so as a company, our goal is to minimize these errors. So what we bring into the community is first this tool here, and I'll mention a couple more tools. This is iDesign spec. So what we've done is we have a solution to centralize the creation, the design, and verification of the register spec. The register specification and memory maps, that's a big part of the functional spec. And typically, huge SOC teams, these IPs could be in IP exact, system RDL, could be in Word or Excel, or some of our customers have actually even said that some of them even exist via email. Okay, so we don't want that. So what we've done here is we've centralized the creation of that. The top level, the SOC level could be in Word or spreadsheet, and then the IP level blocks could be referenced from the different file formats there, as you see from the top: system RDL, IP exact, even YAML, CSV. What we have here is the add-on to Word and Excel. Okay, and from there you can generate basically UVM reg model, RTL. The RTL, we include the widget for the buses. For example, at the IP level, the user can generate the widget for the APB bus, and then as the user migrates to the system level, the user can easily change that to an AHB bus. So we abstracted the bus from the design. So including, in addition to the UVM reg, we also generate the C headers. Also IP exact, we can output IP exact and system RDL, and of course the documentation. So what we've done is any changes, of course, any changes in the functional spec can easily be controlled, right? So any changes, for example, in the Word can easily be tracked and controlled by the user, and then any changes there, you can see the impact to the rest of the downstream code, and you can easily analyze which code could change, and you can easily reflect the changes to the output code. Okay, so that's our goal, and this is actually our flagship product. The next one is the code generator for the UVM test bench. So based on the UVM reg model, we can generate the complete UVM test bench. That includes the sequences, the basic sequences for special registers, also the agents for that. And our goal is to provide the entire UVM test bench with the makefile verification plan to give the user the ability to achieve the 100% functional coverage. And we also include not sure if it's mentioned here, we include we also generate the system Verilog assertions for formal checking. Okay, so we're working with some partners for that. So this is okay. This one here is the one that I'm going to talk about in this presentation. This is iSequence spec. So this is the third one. So basically, the idea of this, the concept of centralizing the register specification, we've done the same thing for sequences. So sequences are very critical in the functional and the test of an SOC. So a lot of our engineers write sequences all day long. So what we've done is we centralize the creation of that from a spreadsheet or spreadsheet format. So they don't have to learn any language. It's in pseudocode, so they can just simply capture the pseudocode of the sequence. I'm going to show an example of that later. So from there, of course, we have the syntax and semantics checker from the tool, and from there, the user can simply generate the target language. It could be C, System Verilog, or UVM. Okay, so from there, we generate those code. So that's also about centralizing the creation of the sequences. Okay, and this is the tool that I'm going to talk about here about the implementation level tests for PSS tools. So as we've heard from Brecker, so PSS, we really believe in PSS too. We don't have a PSS tool, so as I mentioned earlier, we don't have that. So what we do is we augment PSS tools. So we see PSS, the powerful concepts of PSS are abstraction and reuse, and the industry, they really like that. PSS is very useful for creating high-level test scenarios. Within PSS, there's what's called actions, and those are key abstraction units. And inside actions are exec blocks, and the exec blocks are actually the blocks where the implementation level tests are defined. Okay. So Vayav talked about HSI. This is an aspect of HSI. I'm going to talk about this because the registers are fundamental to the IPs, and the registers are quite fundamental to the SOCs. So I'm going to talk about this aspect of HSI. So basically, the way we see this hardware-software interface, you can see at the center is the interconnect fabric. And in the interconnect fabric, of course, there's the CPU on the software side, and then the IP slaves on the hardware side. So there's a lot of embedded registers on the programmable slaves on the IP. So on the software side, the HSI that we see is the CPU instruction set. So all of those instructions from the software executing on the CPU. On the hardware side, there are the registers and interrupts, as you see here. And of course, you can have a bridge and a APB bus connected to the programmable slaves. Okay. So the reason I'm mentioning this is because these sequences at the implementation level, they call out these registers. Okay. So you can see here's an example of a sequence in UVM for this example. So you can see the rm.tx data. So that's a write to this register tx data via the register model. So you need to have that interface layer in order to make this sequence happen, to this step to be executed. And also there's a write to that control register txen field. Okay, and it's also done via the register model. So the read writes to the registers are critical to the sequence, and so sequences they're built on registers, as you see. So the sequences can contain register field writes, reads, pin manipulation commands, and wait function calls, subsequence calls. So registers, as I mentioned earlier, they exist in so many different formats. And that's very true for any SOC companies, because there's a lot of sub-IP teams who maintain registers in IP exact, system RDL, and the ability to parse all of those files and put them together into the SOC level is not that easy. Okay, so our proposed solution is actually to create a golden spec for the implementation level sequences, so that the user can auto-generate the code for the implementation level test sequences for PSS tools. So we can take care of the high level of abstraction, which is devoid of any implementation detail, the control flow. The layer can have access to the hierarchical register data because we have the full information of that register map and memory map. Okay, so this is the tool that I'm mentioning is iSequence spec. So it's basically the same thing as iDesign spec. So the entry is either in text-based entry, okay, or spreadsheet entry, and I'm going to show an example earlier. And then from those different inputs there, you can simply reference those register inputs and then generate these outputs. And these outputs could be for the implementation level sequences for PSS tools. So the proposed tool flow that we have, so we once again we augment these PSS tools. So the first one is to capture the sequences in pseudocode in the golden spec. It could be a spreadsheet again, and then the tool, let the tool generate the sequences in multiple formats, whatever the target platform. It could be C for the firmware team, or system Verilog, or UVM, and then the tool the PSS tool user creates the test scenarios there and calls the action blocks generated by this tool, by iSequenceSpec. And then the PSS tool user would synthesize the test scenarios and generate the required files for the target platform. Okay, so this one is an example. It's not really clear here. So this is a scenario created by the user in the PSS. You can see the component there for UART. Okay, and this ISS sequence here is the component, and then you can see that declaration there, declaring the UART TX implementation level sequence. So the user creates this in the PSS tool. This is our tool. So this is our spreadsheet. So the spreadsheet, if the user is using the spreadsheet, it's basically we have these templates, simple, easy to understand templates. So you can see the sequence name there, URTX on the top. At the bottom there, you can see the steps for the sequence. So you can have for loops there. You can write that. So that's the step there, write TX data, and you can see the value there, right? So from this, we can generate the required files. It could be a C or a system Verilog sequence for the PSS tool. Okay, so this is an example of generating the sequences in the target format. So this file is actually the .pss. Okay, so you can see the component ISS sequence there, and that's the action block, and you can see the header calling that URTX and that mustache notation there. Okay, so we generate this file. We also generate this C code. So C code is the target file format for the firmware. Okay, so you can see the generated code. This is the URTX sequence generated. So that's an auto-generated code that could be used within the PSS tool. This one here. So the first one was a C code. This one is the for the SV tasks for verifications. So same thing. So you can see the task there for the UART TX. Okay, so this is the auto-generated code. That could simply be used by the user. This example here is a UVM sequence output from the generator. Okay, so same thing for the URTX. And so the user generates the stimulus from the PSS tool. Okay. So the PSS tools, they're really good at the generating the test scenarios at the high level. The implementation level tests are coded in the exec blocks. Right now, users have to manually write those. So of course, the main benefit of PSS is to automate the entire flow. So we'd like to be a part of that. So we'd like to generate these implementation level test sequences. iSequenceSpec, it's already in production. This solution that I just talked about here, this is new. Okay, so this is a new flow that we just developed. So it's not used yet by any customers that we have, but iSequenceSpec is. Okay. So so that's again what we want to do is we want to augment PSS tool. Okay, we want to augment it so that the full automation flow that's promised by PSS would be complete. So we want to generate those implementation level test sequences at the low level. Okay, that's it. Thank you.